Now.
Welcome, everyone. I think we can get started now. I'm Tony Roskilly. I'm Professor of Energy Systems at Durham University and a Director of Durham Energy Institute. This event is organized through the EPSRC network, which is for hydrogen fuel transportation. And this is part of a series of webinars associated with hydrogen research and development in the transportation sector. So this week we welcome two speakers who will present the challenges of introducing hydrogen transportation from an industrial perspective. So I'd like to introduce our first speaker, Paul Andrews, who's CEO of OakTec. Paul is involved in the innovation and product development business, specialising in solutions for fuel efficiency and emissions reductions for small and medium-sized combustion engines using clean gas fuels. Paul has been active in leading-edge low-carbon power system innovation for 20 years, having led groundbreaking projects in clean energy technology, hybrid vehicle energy recovery and alternative fuels, including biogas and more recently, hydrogen. So over to you, Paul.
Thanks, Tony. I'm just going to give you an overview of who we are and what we do and our growing interest and work in the area of developing hydrogen-fueled powertrains. So the core technology that OakTec has developed over the last actually probably 10 or more years, we now refer to as clean air gas engines. So we began developing gas engine technology over 20 years ago. At the time, it was primarily for our own interest and entertainment. We used to do things like the Shell Eco Marathon, and we built small gas engines to power fuel-efficient vehicles. But more recently, around 2013, we were able to access funding from Innovate UK and other bodies to take us on the path that I'll sort of describe in this presentation. So primarily we are we have been a technology developer, but we're now moving into the commercial phase. And we have the first orders for some of the technology we've developed over the last few years. We began by developing a novel combustion engine, four-stroke engine technology, which we refer to as Pulsar. And very early in that process, realised that the engine concept worked very well with gas fuels. So the R&D that focused on has looked at LPG, bio-LPG, biogas, more recently hydrogen, and every gas fuel in between, and mixtures of gas fuels. So with a wide range of knowledge and experience of how gas works in a combustion engine. So Cage focus, certainly in the last 4 years, has been on emissions. Gas fuels have obvious advantages with sort of clean burning characteristics. So emissions has been the primary performance criteria of everything that we've developed, and obviously a focus on efficiency and trying to match diesel engine or exceed diesel engine levels of efficiency. So Cage technology is the result of 8 years of R&D. The focus of all the technologies we're putting into UK markets currently is for displacement of diesel with clean gas engines, and we're developing engines to be direct equivalents of diesel and petrol engines. So you don't need to alter the piece of equipment. You take a diesel or petrol engine out and you put a Cage gas engine in. And the first sort of technologies have been on trial initially with HS2 in Euston in generators, powering site welfare units. And we're just about to begin the trial of our first hydrogen engine product on Orkney next month. So just to explain what is a Cage engine, the focus of everything we're developing at OakTec is in the smaller end of the engine scale, so sub 100 kilowatts, but typically between 2 and 50 kilowatts. And the reason for that is, firstly, for a small business with a relatively limited resource, it's easier to develop small engines than large engines, but also there's a gap in the market because of the way the small engine industry is dominated by global OEMs making massive volumes of product at low cost. This sort of would be considered very much a niche to that type of manufacturer, but it's a niche that a small company with high technology can step into and actually achieve quite significant market penetration before the global OEMs take serious interest. In the larger engine sector, there are industrial engines, so a lot of the sort of European and Japanese large industrial engine manufacturers make gas engines, but there's very little technology in this and product in this small engine space. So our technology, we developed a lot of the IP that we are now commercializing on our Pulsar novel engine, but realizing that getting a completely novel engine into the market and going through the whole industrialization process and the level of detailed R&D to do that was going to be very costly and take a lot of time. And even though that technology is sort of a pre-production prototype stage, it's a long way from being able to address large-scale market opportunities. So what we've done is taken a lot of the pieces of technology we developed around the Pulsar and applied it to more conventional engine platforms. And that allows us to buy engines on the directly from manufacturers in reasonable volume and then retrofit our technology to them. So all the engines we build are designed to meet the EU Stage 5 emission standards. So most of our current activity is actually non-automotive. It's for industrial applications, and Stage 5 is the emission standard. And our focus is on minimising oxygen, carbon monoxide, hydrocarbons and particulates, and obviously by making the engines efficient, reducing the CO2 emissions as far as possible. Burning carbon fuels, obviously there will always be CO2 emissions. The engines are all intelligent, fully digitally controlled, and a lot of our IP in these applications is in the control of the combustion and the combustion strategies that we've developed. They're as powerful typically as an equivalent size petrol or diesel engine, but with vastly superior emissions. And a key area, something that Tony mentioned in his introduction, years ago we did a lot of work with hybrid vehicles, and we were developing hybrid vehicles in motorsports 15, 17 years ago, so well before it became a sort of norm in places like Formula One. So we have a lot of knowledge about batteries and energy storage, and we're now integrating cage engines with hybrid systems, so using renewable sources such as solar and wind and battery storage. As we developed our engines, even as long ago as 2012, 2013, we always said that the engines were hydrogen sort of compatible. We'd actually never done any detailed R&D. We'd experimented a little bit with hydrogen, but there hadn't been the need or the demand all the time and funding to do serious R&D. But we could see the hydrogen landscape changing and the opportunity emerging. So in 2017, we were doing an Innovate UK project, and we actually asked if we could do a slight change of scope to do a work package to design a dedicated hydrogen engine. At the time, my son was doing an internship from his engineering masters, so he was here for a year. So under the guidance of our senior engineers, he designed the one in the picture here, and this is actually based on the Pulsar concept. And that engine was a clean sheet design, and we put it on a dynamometer, and within 10 minutes of commissioning it, it was producing 0 NOx emissions and about the same power as the petrol engine the bottom end of the engine is based on. So it was a really successful first sort of stab at the technology. And unfortunately, because we've got all the control systems and understanding of the combustion processes, we knew exactly where to go to get the engine working. So we took that engine and we showcased it at some quite high profile events. So I think the photograph here is at the European Energy Show in Paris with Innovate UK. People were interested, but even, I think this was in 2018, it was still seen as a bit of a curiosity. At the same time, we then built 2 further prototypes and ran one of them in a vehicle. So to actually give a bit of profile to the work we were doing, to show people it would actually work in a real environment. So this is the vehicle. So we actually had this buggy that we developed in a project to demonstrate LPG and then biogas. And we took this vehicle to quite a few events, which is why we put the Union Jack logo. It was about the time that UK government was producing or was using the Union Jack logo to promote a lot of UK industry and innovation. And we thought the best way to demonstrate the hydrogen engine was to build it into this working platform. So we integrated, I think this is the 3rd prototype that we built into the vehicle. So the hydrogen tank, if you can see my cursor, is actually mounted in the frame above the engine, and this is the hydrogen pressure control, and it feeds into a fuel injector. And the engine worked amazingly well, considering it was a prototype developed over a few months. The small fuel tank only allows it to run for about 10 minutes, but it is a working and driving vehicle, and the vehicle is still available for events and demonstration. Its moment of glory was going to be at the Houses of Parliament when Boris announced the move to net zero. But of course, that fell in the middle of the COVID period, so the event that it was due to be the star attraction was cancelled, so it never actually got its moment in the limelight. So just some things we've learned about hydrogen in a combustion engine. It's completely different to burning any other conventional fuel or any gas fuel. There's quite a lot of challenges in making hydrogen work well in a combustion engine. And one of the key factors, or the key factor, is the speed of burn. So roughly 10 times faster than a conventional gas fuel such as LPG. I mean, a lot of people's first thought, people who understand about engines, first downside they see to the adoption of hydrogen is the production of NOx in the combustion process, and hydrogen in the wrong combustion state in an engine produces an awful lot of NOx. The combustion is quite difficult because of the speed of combustion. It needs very precise control, so you couldn't run a hydrogen engine through a conventional carburetor. It needs a very precise digital regime to manage the engine. And it can easily run away if the combustion can run away if hydrogen is introduced into a hot environment. So if you get hydrogen slippage, for example, into a hot exhaust or into a catalyst, it will auto-ignite. So it's very easy to get pops, bangs and backfires in a hydrogen engine if it's not controlled properly. In our second prototype engine, we did occasionally get some runaway combustion events where the combustion became unstable and the engine started auto-combusting. So we know how to eliminate that characteristic. A factor of the speed of combustion, it allows the engines to run completely different combustion strategies to conventional fuels. So having mentioned the NOx emissions, one of the great attractions of hydrogen is you can run ultra lean combustion. So you can run a long way from the ideal air-fuel ratio to produce maximum power. And in fact, we can run engines that run all the way from 0 power to the preset limit of the engine without a throttle. So you don't need to control it. A bit like a diesel engine, you don't need a mechanical throttle to alter the air-fuel ratio. We've realised, actually been quite surprised by how thermally efficient we can make the engines we've developed. And one of the reasons for that is the combustion is so complete, the heat losses are lower, so the exhaust temperature and the oil temperature, so the waste heat being absorbed by the engine is lower than a conventional engine. So that's obviously quite a strong advantage in utilisation of what's quite a difficult fuel to transport and store. And then, as I mentioned earlier, a well-developed and calibrated hydrogen engine can be broadly comparable in its performance to a petrol and diesel engine. And just a caveat around that is I'm particularly talking here about the type of industrial engines that we're dealing with. So an engine in a generator runs at a steady state and is relatively light loaded compared to a high performance automotive engine, which requires different sort of characteristics. So this is a project we've been working on over the last 6 months, and it's the Innovate UK's decarbonising of the maritime environment. So we've been working with the EMEC consortium up in Orkney, and we've built our first sort of pre-production hydrogen engine into this generator, and the generator will power a solar hybrid temporary building that will sit on the Kirkwall harbour side, and it's been designed as the cruise ship reception building. So when the cruise liners come into Kirkwall, the first on-the-shore experience of the customers will be in the reception area, and the reception area is powered by this hydrogen generator. So the roof of the building has a solar array, and then through a series of inverters, there's a battery energy store, and the generator effectively only operates when the state of charge of the batteries falls below a predetermined point. So this particular engine is a 400cc single cylinder engine. I mentioned in my earlier presentation that we were surprised at how efficient we could make these engines, and this at 4 kilowatts electrical output is around 40% thermally efficient. As the electrical output falls, the efficiency falls with it. And unfortunately, the batteries in this particular unit are lead acid, so we can't charge it much over 2.5 to 3 kilowatts, but it still gives an insight into the potential efficiency of the engine and the engines as we further develop them. So as we've talked about, the engine is calibrated at 4 kilowatts to have 0 emissions other than water vapour. If anybody wants to look at that project, the project is called HyMet. It's a multifaceted project that's looking at a lot of opportunities for hydrogen in the marine environment. So to run this unit in the building, we use this, what they call an MCP, which is a store of vertically, these bottles are about 2 meters tall, and there's 9 of them. I think the hydrogen pressure in these bottles is about 200 bar, but this unit will power the building for, we hope, 2 to 3 weeks, obviously with the addition of the solar power helping reducing the fuel use. So that unit is actually now installed in or the generator is installed in the building unit, and it will be deployed on the last day of March, which is the end of the project. It will be trialled throughout the summer, so the whole of this season, the cruise terminal should be powered by this system. So OakTec has a new commercial business which is called Cage Technologies Limited, and we're now developing this particular engine, and we have a range of follow-on engines that we're developing as commercial products, and we're hoping to be able to sell these in reasonable volume over the next 2 to 3 years. So those are my contact details. If anybody wants to get hold of me, the email address is there, and my phone number. I'm happy to talk and engage with anybody on this topic. And thanks everybody for hearing me out.
Thanks very much, Paul. I'm sorry for the glitch with the presentation.